Hello, everyone, and welcome to our 10th session in 2021 of this live stream series, Exploring 3D Experience Works. My name is Gian Calisi. Here with me, as always, is John Martirano. We're a couple of industry process consultants working for Dassault System SolidWorks out of the Waltham office right outside of Boston. Uh, so if you have any questions or comments, or you just feel like talking to us, you can go ahead and engage the chat on the right side of the YouTube video. So you'll see the video, kind of to the center to the left. You can engage with us right there, and we'll be checking that periodically to make sure we answer any questions in there. So thanks again for joining. And if you're new to the series, you might be wondering, what is 3D Experience Works? What is this thing that you're about to explore with us for the next hour or so? Well, 3D Experience Works is our growing portfolio of tools handpicked by SolidWorks to solve just about any product development challenge that you might face. So this is 3D Experience Works, what you see on screen right now, kind of our five core brands that all make up this portfolio. And when we talk about tackling the product development process, um, that process can be whittled down to mainly three stages: planning, developing, and releasing the products that you design. And we know how well SolidWorks can tackle that second step, develop, as you create your designs from scratch in there and simulate and everything. But the rest of the brands that are a part of the 3D Experience Works portfolio all kind of sprinkle in and provide that one-stop shop of connected solutions, each bringing their own unique value to the table. So if you joined us at all in 2020, then we've been all over the map covering different workflows, different products in these different phases of the product development process. But today we're going to be revisiting one that we did a high-level overview of, Simulia, and some of the cloud-based simulation or cloud-connected simulation tools that Simulia brings us, all built on the Abacus solver. And today we're revisiting that with our special guest. I'm happy to welcome with us Sashi. How you doing,
Welcome.
Sashi?
Hey, Gian. John, how's it
Hey,
going?
going great. Look, very happy to be looking at some cool new simulations today.
Yeah, for sure. Um, you know, the last session that you guys had, I did sit on it, and it was such a good session, and it really covered, like you said, at a broad level, all the simulation tools that we have on the 3D Experience platform. Today we're going to take a little bit of a deeper dive to see how simulation can be integrated into the engineering environment to enable collaboration, right? So in today's engineering world, um, simulation is so much more than just running the simulation and looking at the results, right? We want to try to collaborate, get as many stakeholders involved as possible, and to drive innovation, right? With all the different types of simulation that you can integrate into that engineering environment. With that said, I wanted to introduce our model today, which is going to be the Beamy model. Some of our audience might have seen this model before. So this is a compact projector. It is wireless. And if you take a look at what's internal to this Beamy model, it has a lot of components, right? So it has the speakers, it has the batteries, the PCB board, the covers, right? And we think about making a product like this. It involves a lot of different people, right? A lot of different teams have to collaborate to put out a product like this. Um, and when we think specifically in the industry that the Beamy model would be in, that the high tech industry, this industry has become a very, very competitive industry, right? Um, there has been an exponential increase in smart and connected electronic devices, right? So when you think about IoT, cell phones, even your refrigerator, right, is a connected device today. So it's becoming a very, very crowded and competitive space. And then within the products itself, within the silo products, there's extreme competition offering broader and innovative portfolios, right? So, think about, if you have a cell phone released 10 years ago, your smart cell phone, the companies used to only put out one version every year. But nowadays, the companies are putting out multiple versions for every release, right? So, and think of that from an engineering perspective, right? So they are releasing multiple versions every 12 months, right? So, think about that data management and all the testing they have to do, the prototype testing, the simulation. It can be quite a challenge. And then, cutting edge technologies in semiconductor for compact and complex products, right? So if we are keeping up with the news, we know that there is a shortage on semiconductors today, and this has actually caused more of a competition, because companies have to now put out the best product they can, right? They really can't waste their resources on products that might make it, might not make it, right? So they have to put out the best version they can due to that scarcity in
Most
semiconductors.
definitely. I mean, consumer products are really far behind right now. I know at least my friend, he has this truck, and he ordered this new truck, and it has all the bells and whistles. So it requires a lot of these semiconductors for all the electronics to work, and they're over a year out, just in the supply chain of these semiconductors alone. So I mean, it definitely is a big industry trend right now. I'd have to say, I have to agree with you there. It's going to be expensive. Yeah, absolutely. Yeah. So I mean, these are definitely some relative challenges of the industry. How are we going to encompass that in the Beamy story?
When we look at the BME, so much engineering that goes into this, from design to simulation to prototyping to manufacturing. But when we think about simulation specifically, we have, of course, our CFD analysis, right? So this the BME model has a PCB board, it has chips, it's going to heat up. We're going to make sure that we have proper ventilation. We're going to make sure that it doesn't overheat and start melting the chips, right? And then it will essentially stop working. We got to make sure that we have proper ventilation in there. And then, being that this is could be considered a handheld device, right? Because it's portable, it's wireless, it's something maybe you put in your bag and you travel with. And there's a saying with portable devices, it's not a question about if it's going to drop, it's a question about when it's going to drop. So we got to check for structural integrity of the product. And then with compact electronic products like this, especially wireless products, we have to check for the electromagnetics aspect of
Uh,
things, right? So, so when we look at this tree, these three types of simulation, this is essentially required for a product like this, right? So we have, our thermal engineers, we have our structural engineers, and we have our electrical engineers. And then we also have our design engineers. So we have 4 teams that are working together to create this product, right? So, so having to run the analysis and make design changes based on the analysis, how do you work in that environment? How do you work in that collaborative environment is essentially going to be our conversation today. And the best part about all of this is that with the 3D Experience platform, you can actually run all of this analysis using the same data set on the same platform, right? So we can ensure that everybody is on the same data set at all times, whether it's revision changes or any design changes, they can essentially rerun the same analysis over and over again, and everybody would be, all the different teams would be on the same page. So I'm going to actually start off the presentation with the CFD analysis. Now, why do you think that is, John?
Well, that's a good question, but I mean, I could guess that maybe we don't want it to be too hot, right? Maybe it wouldn't work. That's a problem.
And the EM stuff as well, right? So let's take a look at our CFD solution on the platform. So what we have is our fluid dynamics engineer role. So all our products on the platform are called roles. And the reason for that is because we believe that the product should meet your role, and we essentially integrate all the features and tools to meet your requirement within that role, right? So when we look at the fluid dynamics engineer role, we offer a CAD and PLM embedded CFD for flow and thermal performance simulations. And this accelerates product innovation in a collaborative cloud environment. And when we look at it specifically for the BME, a thermal engineer would want to check for component temperature, right? So specifically the PCB board, the chips, the heat sink, and then also the airflow, right? So we want to ensure that we have good airflow flowing into the model and then out of the model as well to keep that at a steady state temperature. Now, when we look at the role itself, the fluid dynamics engineer role, it does so much more than just component or airflow type of analysis. From a thermal perspective, we cover all different heat transfer, so conduction, convection, and radiation, surface to surface and solar radiation. In terms of modeling, we do multiple reference frames, MRF. We model fans, baffles, porous media. So if you think about it, with the fans and baffles and porous medias, the electronic component models, becomes a really good fit for this role. And in addition to that, we also have joule heating with this solution. And one other feature that we have, which is really great, is the ability to map the structural role for thermal stresses. And I cannot stress this enough, that with a product like this, we have to run thermal stresses because of the varying temperatures and varying materials and components that we have in this product, right? And sometimes the thermal stress might be run by the thermal engineer, or sometimes it might be run by the structural engineer, or sometimes the one engineer might be running the CFD, the structural analysis, and all of the analysis, right? But being that all of these solutions are on the platform, on the 3D Experience platform, you can actually just reuse the same data that you got from your thermal analysis to run your thermal stress analysis. In fact, we can even just run a thermal stress analysis directly in our structural analysis tool. So there's so many different variations, but what's important is being able to reuse the same data over and over again.
Great. So
In terms
flow.
of flow, we provide steady and unsteady flow. We can also handle incompressible and compressible
Ah,
flows, as well as Newtonian and non-Newtonian fluids and gases and
so a
all of
lot
that.
of applications here, just by looking at the compressible, uncompressible flow. So that has some aerospace applications. So we are using the Beamy model today as an example. However, that's not there. There's so many example. However, that's not there. There's so many more. There are limitless options that we have to use this. Right? Is that right, Sashi?
Yeah, exactly. So this fluid dynamics engineer role can also be used in aerospace, automotive, right? I mean, a number of applications, right? So for some of you who joined us in the last session that we covered all the Simulia tools, we actually showed some examples of using this role in an aerospace or automotive space. So for those of you who didn't watch that session live, you can actually watch the recorded session on our SolidWorks YouTube page.
Great.
So with that said, let's actually jump into the example, the Beamy model example, right? And the first thing I wanted to talk about is what does the workflow look like going from SolidWorks to the 3D Experience platform, right? So I assume a lot of people, on this presentation today are using SolidWorks to design their models, and SolidWorks really is where the idea becomes a reality, right? So when we look at the first few steps, we have the model in SolidWorks. We save and transfer that model to the 3D Experience platform. We can launch the fluid scenario app, which is part of the fluid dynamics role, to set up the simulation directly within SolidWorks. That brings us to the platform where we can set up the analysis, execute the analysis, and then post-process the results. Then, depending on the results, you might make some design changes, right? As we call it, simulation-driven design, right? So you could run through that iteration multiple times, right? Looking at your results and making design changes to get you to the best design. At which point you can then, once you've gotten to the best design, you can, make that decision to move to the next step, right? To manufacturing, to prototyping, and be confident with your design. So first up, we're going to actually take a look at the first 4 steps, right? Opening the model in SolidWorks and transferring it onto the platform. So let's take a look at what that looks like, right? So we have this Beamy model in SolidWorks, and you can see that it has all the components, the speakers, the batteries, the PCB board. It's all there. And right within SolidWorks itself, we have our 3D Experience add-in, where here is where we can actually go ahead and right-click that top level assembly and hit save. Now, when we hit save, it will automatically save the model to the platform. So, and not only does it save the model to the platform, it also creates a link between the model in SolidWorks and the model that we will essentially have on the platform to run the simulation. Now, this is key. This is important because this enables us to make design changes and easily push those design changes to our existing simulation. So we don't have to rerun or reset up simulations, even with design changes. So we can run, multiple versions of this model within the same analysis. So that's a huge time saver. We can just kind of keep rerunning the simulation. Now, like I said, right within SolidWorks itself, we can actually launch the Fluid Scenario Creation app, which is part of the Fluid Dynamics Engineer role. And this will essentially bring up the 3D Experience interface, and then we can start setting up our simulation in the 3D Experience platform. So now we have the model here and we are in the platform. We can go ahead and start setting up the simulation.
So Sashi, is it like is the setting up or the setup of the model, is that something that, maybe is easy to do? Is it intuitive, or is it, how is it? How's the setup process? What does that look like?
I mean, that's a really good question, John. I mean, that question comes up all the time with simulation, right? And one thing that's super important to us when we were, creating this simulation solution on the platform was to make it as intuitive as possible for the user, right? So we wanted to make it a very, very straightforward tool so that anyone that uses it, especially SolidWorks users, will be able to navigate the interface, in a very, very straightforward manner, right? In addition to that, we also have some interactive tools to ensure that even beginners can easily, can start using this tool almost right away. So let's actually take a look at what that looks
Great.
like. So you can see here, we have our assistant tool, right? So this assistant tool, which can be used by beginners and even advanced users, enables you to step through the basic properties and parameters needed for this simulation, right? So right now, for the first step, it's asking me to set up the to specify the materials for the model. And then the next thing is it says specify what type of analysis it is. And then the next step is it will say, specify what are some of the initial conditions, right? Is it in room temperature? Or is it at a much higher temperature to start with? Are there any initial flow conditions that we need to consider, right? And as we step through this assistant tool, you can actually see there's a green check mark there, right? And what this green check mark does, John, is it gives me the confidence that I'm actually setting up this analysis correctly, right? I don't have to memorize every step of the way, right? It's just kind of guiding me through the simulation.
And a green
So,
check mark is
like I
pretty
said,
universal, good to go. So hard to mistake that for something else.
yeah, exactly. And that red mark means
Yeah.
stop, right? Stop.
Yeah.
Take a look at it. You need to do something with that, right? So, and like I said, right, so this can be for beginners who are just starting off, whether it's starting off with CFD analysis in general or starting off with this role, or even advanced users, right? Even for someone like me, I use this role all the time. I still use the assistant tool, and it's just because it's a huge time saver and it enables me to step through all the tools right from this assistant panel rather than having to go look for all the icons. Okay, so now that we've set up the materials, the physics conditions, the boundary conditions, the zone, the loads, the context, the next thing we need to do is mesh this model. Actually wanted to spend some time on for some of our advanced users on this presentation today. So we actually have quite a bit of advanced meshing tools provided on the platform, and we can even combine different type of meshing. We can combine our hex meshing and our tetrahedral meshing, and this is very, very important, especially with CFD analysis. And we also provide tools to easily select and localize different mesh settings as well. And what I mean by that is, take that heatsink, for example, right? So this heatsink is a very, very critical component in our assembly here, in our simulation model here, right? Because that heatsink sits on the main chip that powers this BIMI. Now, I need to make sure that that heatsink is at a acceptable temperature as well as the chip underneath it. So you can see that I actually have a very, very dense mesh around the heatsink and even in between the fins, right? So I'm going to get very, very good, accurate results around that heatsink and that chip, and that's very important. That's really my goal for this simulation. Now, the void area or the dead space that's around, within this enclosure, I probably need a decent mesh, but I don't need a super dense mesh like I do around the heatsink, right? So something that will just give me decent results, just making sure that that the airflow is still within room temperature, it's not overheating. That's really all I need to know. So you can see that I have actually different mesh settings, between the heatsink and the air around the heatsink.
Yeah, so don't waste those resources essentially where you don't need them.
Exactly. And resources really is the key word here, right? Because when it comes down to it, techniques like this is going to enable you to run your simulation much faster and get those results much quicker. So then you can make those engineering decisions quicker as well, right? As you cycle through your product development, you cycle through your
Great.
product
So what comes
development.
after mesh?
Well, now we've completed the simulation setup. So now you have to execute the simulation, and then we can post process the results, right? So we can take a look at the results and then decide how we can move forward from that point on, right? So to execute the simulation, we actually have a few different options for our users, right? So we actually provide access to high power computing on the cloud for complex and large simulations. So, especially with the CFD analysis, right? Sometimes you might be running pretty heavy duty analysis, right? Like we talked about earlier, like aerospace and automotive. In cases like that, you might want to tap into some high power computing, and we have access to that. So, having this role on the cloud enables us to tap into hundreds and hundreds of cores, right? So we provide that option, but it's not always necessary to have high power computing, right? So for maybe this analysis with this BME model, maybe I just need maybe few cores. What comes with my hardware. So we also provide local embedded compute available up to 16 cores, as well as up to 16
And
cores on the cloud.
that's a lot, right?
And
Because I mean,
that's
I think my computer has something along the lines of like 7. So that's a decent number, right?
Yeah, so most engineering computers today, I would say, ranges between 4 to 8 cores. And you could run pretty good analysis within 4 to 8 cores, right? And what's nice about this role, and this is quite unheard of, is that we provide 16 cores without any
Wow.
additional charges. So for some of our users that have already invested in hardware that perhaps has like 12, 14, 16 cores, they can use all of those cores without any additional charges. Now, let's say for a user that has a machine that, let's say, only has 4 cores, they can run up to 16 cores on the cloud without any additional charge as well. So many different options here to ensure that you get your work done, at an acceptable, time. Um, and then, of course, last but not least, we talk about cloud. I think the question about how secure it is, all of that comes up. I always like to put this out there, John. Right? I mean, DS has made a commitment to secure data. Right? So we have the highest level of data security when it comes to on the cloud data. So there's really shouldn't be any concerns in terms of data
Absolutely. I
security
mean,
on
I'm
the
sure
cloud.
people would be very happy to hear that. Um, yeah.
Absolutely, absolutely. All right, so let's take a look at the results that we have here. So you can actually see this result looks amazing, right? I mean, this is the type of results that you will get, running your simulation on the fluid dynamics engineer role, and you can also process your results on the cloud as well. So so let's say if you want to get this very very swanky, graphical results, you can, and you can use those cloud computes as well. So taking a look at the results here, we can actually dive deep into the results, right? We can even output some very very accurate graphs, and you can actually see how much time it took um, for the chip and heatsink to reach steady state. And right now we are looking at 130 Celsius for the chip, and that to me is kind of high. So we really wanted to shoot for under 80 Celsius. So 130 is kind of high. And when we think about products like this, these consumer product, compact electronic products, they usually there's quite a big factor of safety there, right? So it could run maybe at maybe 120
But why
Celsius
would we
without
want
any
to
issues.
risk it?
But
On like a hot summer
and
day, I want to be able to have my projector in like the desert, and it still work for me.
yeah, exactly, right. we can control, right? If you're, if you're going to be in a room that has a lot of computers and just the room temperature is high, let's say the AC is broken and the temperature starts to go up and the temperature spikes in the room, the electronic component should be able to withstand that, like a sudden spike in temperature. But can it sustain running at a high temperature over multiple hours? Maybe not. So we want to make sure that we are running this system at a acceptable temperature. So in this case, we want to make sure that it's under 80 Celsius, right? So yeah, so this is what we talk about in terms of running that iterative process, right? So now we have the results, and now we can make real engineering decisions based on those results. So in
Hey,
this
Sashi,
case,
before we jump into making design changes, I was just wondering, how long did it actually take for you to run that simulation? That mesh looked like it got pretty bulky, so I'm just curious as to how long that might have taken in the cloud.
yeah, that's a really good question, Gian. So, for this model, we actually did a few different benchmarks, right? So, running it on my computer, local hardware, it took about 2 hours to run on I think I have like a 8-core machine, like a 2 hour to run, but this is very, very in-depth analysis. But guess
Right.
what? When I ran it with 16 cores on the cloud, it dropped
That's
to about
insane.
24 minutes.
Wow.
So I haven't even tapped into that high power computing. Now the high power computing, I think we have about
Wow.
280 cores on the cloud. Yeah, that would have brought that number even lower, right? So under an hour, I can run this, solve it, get my results, and move forward with
Great.
my engineering work.
Awesome. Yeah, one more question just about the mesh. I'm just wondering how those brick elements, how they compare to something like SolidWorks flow simulation. Is it comparable to the same kind of meshing, or could you speak to that a little bit?
Yeah, so with our flow simulation in SolidWorks, I mean it's a it's a really good tool. I mean and what we've done with our fluid dynamics engineer role is to ensure that it's at the same level as our flow simulation tool in SolidWorks. So
I
when we
see.
look at what we have on the platform, it enables high power computing, which is what we don't have on with flow simulation today, right? So high
Right.
power computing, that collaborative aspect, as well as scalability, future scalability, right? So just being able to use our tools on the platform with other tools on the platform, like what we're going to show shortly here with our structural analysis tool, right? So, so there's some added benefits to going onto the platform, but like I said, the flow simulation tool is very good, and our fluid dynamics engineer
Great.
is
So,
comparable to that.
Sashi, kind of where we
Awesome.
left off was, we just showed the results. Everything was a little bit too hot. So, how are we going to tackle that challenge with the Beamy model so we can get this out to customers without it, melting on them?
Good question. So I'm not going to so at this stage you can see that the design actually looks good, right? I mean, it has that that nice shape to it. It's nice and compact, right? The PCB placement, the speaker placement, the battery placement, it all has a home. So I don't want to go around and make too many changes to the design. So what we can do here is, right, we can maybe introduce something for cooling system, right? So, with electronic products becoming more and more compact, in recent years, there actually has been more development with compact fans, believe it or not. So today you can actually buy fans that are tiny, and you can fit
How
those
small are we talking?
into your compact electronic
Like,
products. And it doesn't really do much in terms of cooling it down. What it does is it diverts the cool air in the right direction, right? So it really does do a good job, when we are trying to make sure that the air that's coming through our ventilation is being pushed in the right direction. So let's actually take a look at doing that for this BV model, right? So So here, what we're going to do is we're going to make that design change. So you can see here we have introduced that tiny little fan, that cute little fan there. And what we'll do is we will actually save the model to the platform as a new revision, right? So if you take a look here, we have 5 revisions. So this BME model that has gone through 5 revisions, right? So maybe the first few were design changes, right? And iteration E1 is, you're introducing a new component, right? So when we introduce a new component like this, so maybe the design engineer made this change and has pushed this new revision to the platform, all of the teams that are working on this BME model on the platform will automatically see this new revision, right? So let's say the structural engineer, the electrical engineer, and the thermal engineer, they're all running their simulations. They are working in that swim community, right? So that's another tool that we have on the platform where everybody can collaborate and post images and post their CAD models and discuss things like new iteration. Let's say the design engineer goes on there and says, hey, new revision E1, run all your ongoing simulations on E1. Everybody will see it. They can actually just go right onto the platform and they can rerun the analysis that they had set up for revision D1 with revision E1. So they don't even have to reset up the analysis, right? So that is a huge, huge time saver, right? So, just being able to change the model, you have to remesh it because you've introduced a new product, and then just hit run and you get your new results. So with that said, let's actually take a look at how introducing this fan has changed the results. So taking a look at the fan, the chip temperature, we went from 126 down to 76.7. So that's under 80 Celsius, where we want to be. And I think the heat sink went from 108 to about 41 Celsius. So that's about room temperature, slightly higher than room temperature, which is exactly where we want to be for the heat sink. Now, this actually makes a lot of sense, right? So essentially what we've done here is that little fan has divert the air, the room temperature air, to blow over the heat sink, right? So the air, that cold air, is capturing all the heat, and it's pulling the heat air, the hot air out, right? So there's an assumption like a lot of people make, when they hear their laptop fans go off and then they put their hand on the ventilation and there's hot air blowing out, means that their system is overheating. Actually, it's not. Actually, it's doing exactly what it's supposed to do. It's pushing the hot air out of your system. So it's working. So whatever cooling system that's built into your desktop or your laptop is working great. If you touch the laptop and it's hot, now that's a different question, right? So maybe the cooling system, maybe you need a better cooling system. Maybe you need to add your own fan or something like that. But in this case, I think the results look good here. I mean, the heat sink's at 41, the chip's at 74. We hit our requirements, meaning that this technology-wise, this works. So now I can actually move to the next stage, which is this product going to be strong enough, right? So we're going to think about structurally how this BME model is going to perform. So from a structural analysis perspective on the platform, we have this proven, robust, and reliable FEA technology that's based on the Abacus simulation analysis software. So for some of you who are familiar with this on the call, on this presentation, and some of you might not be, well, Abacus has been around for about 20 plus, almost 30 years. It's really the product that kicked off our Simulia brand in Dassault Systems. It's one of the best, if not the best, structural analysis software on the market. And what we've done at Dassault System is we've taken that Abacus solver and we've integrated it into the platform, right? So now SolidWorks users can actually use this type of technology. So Gian, to your question earlier, that flow simulation versus fluid dynamics engineer role, with the fluid dynamics engineer role, the users can also take advantage of the Abacus solver on the platform, right? So that this is platform specific, an advantage using the platform. So when we look at what we have to offer in terms of a structural analysis on the platform, we actually have multiple roles versus when we looked at the fluid dynamics or the CFD analysis, we only had one role, right? So, and like I said, our roles typically match your role in an engineering team. So the first role we have is our structural designer. So this enables you to run linear static analysis, frequency, buckling, and thermal. So these are very typical analysis that you run in the early stage design phase, right? So, if you're still trying to decide on certain features, design features, you can run these analysis and you can drive your design changes based on simulation results. The next role we have is our structural engineer, right? So it's a step up from our structural designer with the addition of our linear dynamics functionality. So if you want to run some vibration analysis, you can do that with our structural engineer role. The next role we have is our durability and performance engineer role, which enables running nonlinear static analysis as well as fatigue analysis, in addition to all the other features that comes with the structural designer and structural engineer role. So so if you're dealing with any nonlinear materials or nonlinear conditions for your simulation, this will be a really good role to use, right? It also comes with the ability to integrate complex materials, advanced meshing, as well as advanced contacts, right? So when we think about contact condition, that really is what makes Abacus, as powerful as it is because of how well it handles contacts between different components. And the last role that we have here is our top of the line role, is our durability and mechanics engineer role, which enables nonlinear dynamics. So when we have components like this, as you see on the screen, that are moving like this blade, and we have this damage model, this nonlinear dynamics solver is a really good fit. So for this BME model, the first structural analysis that you're going to run is a 3-point bending test. And a 3-point bending test is pretty important for compact products like this, right? It really is to test for, whether it's for normal wear and tear or if it's being abused. So, so think about your cell phone, right? You have, you buy it, it comes with a 1-year warranty, 365 days. At day 364, I go
Over
and
your knee, just
bend
break
it,
it. Yeah, I want a new one.
try to
Is that gonna work?
try to break it. Maybe I can get a new phone out of it on day 364 or 344. And well, guess what? The manufacturers have tests for it, and they can, without a doubt, tell you that, hey, if you're able to bend your cell phone like that, you've essentially voided the warranty, right? Because you've abused the product, right? That's not normal wear and tear. The normal wear and tear is, let's say if I put my cell phone in my back pocket and I sat down and it bent a little bit, that is more along the lines of normal wear and tear, right? And it usually should still work in that case. It might not look, sleek anymore, right? But it should still work. So that is, that's how you can, from a manufacturer perspective, you can guarantee that, these products are not going to be, not become a warranty nightmare. So for this BME model, I'm actually just going to run the 3-point bending test on the main chassis itself. So this has to be the strongest component. This component is essentially where it holds the strength integrity of this entire product. So I'm going to test it on this. Now for this test, I'm actually going to do something different, right? So the original BME, this chassis was aluminum. So if you look at the design,
Pricey.
design like this would probably have to be CNC machined, which can be expensive and can be time consuming, right? Now, if let's say this BME becomes a hit and I want to mass produce it and bring the cost down, I would probably need to be able to injection mold this chassis, right? So I'm actually going to try a plastic material here, an arclic material, which is a bilinear material. So it's not a linear material. So I'm actually going to use our structural performance engineer role to run this analysis. So you can see I have two fixed rods, and I have a metal rod that's pushing down the middle by 20 millimeters to see if it will be able to withstand, that kind of wear and tear, right? So when we
Hey,
took a look
Sashi.
at the
So
interface,
I know we're focusing on the structure. I'm just wondering, is it possible if we wanted to see if, the inner components would like pop off of this chassis, if we wanted to take a look at how those would behave, is that something we could do here?
absolutely, absolutely. So that is, that would be, I would say, a later stage analysis where,
Right.
what we could do is we can put all of these components together, and yes, we can do a 3-point bending test, we can do a drop test, right, to see, and we can even simulate fastening. So, the a product like this, we typically don't have screws. It's all being fastened together, right? And
Right.
that's why typically when you drop it, it's just kind of the fasteners to make sure that our fasteners are modeled correctly and modeled in the right place. So yeah, I mean this solution really provides an end-to-end simulation solution. All right, so taking a look at this structural analysis, look at the interface. This is the exact same interface that we had for our CFD analysis, right? The simulation setup is on the left, the icons are at the bottom, and the assistant tool, the same assistant tool, is on the right of the screen, right? So this is, to me, a huge advantage, right? So let's say, if I was in a more leaner engineering team and I was running the CFD analysis and the structural analysis, guess what? I don't have to go learn an entirely new product or an entirely new interface or where the icons are, right? So that's one thing that was important to us is the consistency of the platform, right? So having all these different tools that have different usage, but having that same interface and being able to use that same data set over and over again. So we have the history tree. We already talked about the history tree to the left of the screen. We have all our icons at the bottom, and then we have the assistant tool to the right of the screen. Now, taking a look at the results, you can see that what we have here is actually the material actually snaps back into place. So this actually has some give, meaning that because it's bilinear, and let's say if the component is it's in your backpack and somehow it's bent a little bit, like 20 millimeters is not a lot, it bends a little bit, it actually will just go back to its original shape. So there's no permanent deformation for this product. One thing I wanted to bring up here, John and Jan, is that we actually tried to run this in SOLIDWORKS simulation, and we were unable to converge the result due to its non-linearity, right? So SOLIDWORKS simulation does have a non-linear solver, and it has its usage, but in some cases like this, where we're using a bilinear material and a snapback, we were not able to converge the result. So, for some of our users today who are using SOLIDWORKS simulation that's looking for more capability, you can actually step right into that structural performance engineer role today and start actually reusing some of the data that you already have in your SOLIDWORKS simulation. So taking a look at the stress results, the stress is also within the acceptable range. So it looks like, hey, structurally, with the 3-point bending test, as long as the user doesn't abuse the product, we are in good shape, right? So normal wear and tear, we should be in good shape in terms of warranty. Now, another very, very critical test that has to be run for consumer products is drop test. This is not optional. This is a test that you have to run, right? So going back to that term I used earlier, right? So it's not a question about if it's going to drop, it's a question about when it's going to drop, right? So if the consumer is holding it in their hand, they're going to drop it at one point or another. I mean, I know I've dropped my mouse, my phone, everything that I've held in my hand, I've dropped at some point, right? So let's take a look at what that result looks like. So what we've done here, what I'm showing here, is actually an early stage design of that chassis, where it's a little bit more bulkier. And the reason why I wanted to show this is because we actually got really, really good results, right? The stress was very low, the deformation was very low, and that actually means that we've kind of over-designed this component a little bit. So we were actually able to remove material and make this product much lighter. Now, one another big advantage of running a simulation analysis for a product like this is being able to view your results, in very, very close proximity, right? Just being able to really dive into your results. So in this case, we actually created a section view, being able to see what that stress is across the thickness, right? So a product like this will have very, very thin walls. So we want to make sure that it can withstand any direct
That's
force
not something that you can do
onto the
so
body.
easily
So one
with
thing we're
just
able,
regular, prototyping, by actually making the prototype. It's not very easy just to make a section view and not actually, wreck it and actually see its actual deformation.
yeah, actually it's almost impossible, right? So how do you cut through a product to see, because if you change the product in any means, then you change the strength integrity of the product, right? So this is where simulation plays a really, really big role, just being able to really, really dive into your results. So one thing we actually were able to capture here was high stress and deformation around that speaker hole. So when we started designing this BME model, we had a very, very, very tight tolerance around that speaker. So it was almost a snug fit around that speaker. Now, if that hole somehow deformed, that speaker is not going to be held in place properly ever again, right? After one drop. Now, think of it this way. Think those cheap sunglasses that you buy, right? And you drop it, and those frames pop out. Those frames never ever fit back properly into those lens never fit back into those frames properly, right? They will
Right.
always just keep popping out because the frame has actually deformed ever so slightly, right? So it's never ever going to fit the same way again. The same thing goes for this, right? So if that hole now deforms ever so slightly, that speaker is not going to have that snug fit anymore. So running an analysis like this enable us to capture results like that. So of course, we can also run our drop tests in different angles, different directions. One thing I would like to add is also you can run it from different heights, right? So let's say if you wanted to try to figure out, how this component is going to rotate in air, once you've set that gravity and that center of mass with all your components in different location that has different weight distribution, you can very easily find the center of mass even in SolidWorks. But how is that product going to start rotating in air and where it's going to land as you drop it from, let's say, 3 feet, 6 feet, 9 feet, 12 feet? You can do that in this analysis, right? So it'll give you a full perspective of how it's going to be used, how the consumer is going to be using it. All right, so that actually wraps up our structural analysis for the BME model. So the last thing I touch on in terms of simulation is our electromagnetic analysis, right? So this is a new addition to our platform, and it is our electromagnetics engineer role. And this is a high-performance 3D electromagnetic simulation powered by the industry-proven CST Studio Suite. So for any of you out there that are running EMAC simulations, I'm sure you've heard of CST. It's been around for many years, and it's being used by a lot of industry leading electronic companies. And our technology on the platform is 100% CST Studio Suite. So the electromagnetics engineer role enables high frequency and low frequency electromagnetic simulation all within the same simulation role. And this is a huge advantage, right? If you look out in the simulation market, a lot of times these are divvied up into different products. We provide a high frequency and low frequency as a single solution. We can use this solution to optimize antenna and microwave devices, so that the antenna optimization is going to be big for the BME. We can prevent and minimize electromagnetic interference. Again, that's going to be a big one, right, for the BME, and electromagnetic compatibility issues as well. And with the CST Studio Suite solution, we can also run coupled simulations. So, coupling it with heat transfer at a system level, hybrid. We can even integrate multi-physics, where we can combine, electromagnetics and
So
circuit code
Sashi,
simulations
at a
as well.
high level,
Now, being
the
that this
reason why we run electromagnetic simulation is to make sure this BME model is going to play nicely with other devices. We need to know, what type of frequencies it's going to emit, and make sure it doesn't interfere with anything or cause any harm to anybody.
Absolutely, right? So, when you think about the projector, it's interesting, right? Because it has to create this wireless connection with your laptop, right? Where you are maybe running a PowerPoint presentation and you have to project that to the from the BME. So you got to make sure that there's no interference and it's compatible and all of that stuff. As well as, you're right, safety as well. For example, today we are wearing all these connected devices like Fitbits and your Apple Watch and stuff like that. That's on our. So got to make sure that it is an acceptable electromagnetic range, so that it's not affecting us, right, in a bad way. All right. Now, being that this solution is tied to our platform, like the 3D Experience platform, we have easy access to SolidWorks, right? So we can transfer our SolidWorks models right into CST Studio Suite, and it's all connected to the platform. Like the data resides on the platform. Of course, right, the whole premise of presentation is to enable team collaboration, version control, and knowledge capture. It's all on the platform. Because, again, it's on the platform, we can enable that lightweight visualization of results, right? So, we run the analysis, we execute the analysis, and we view the results right in the 3D Experience interface. But you can also view the results right on your web browser as well, right? So, and that's our lightweight results viewer. So, let's say if you're on the road, you're traveling, and you want to take a look at some simulation results, you don't have to pop open your computer and fire up, the 3D Experience platform and all of that. You can actually just, any device that enables you to open up a web browser, whether it's your smartphone or, iPad, you can view your results, right? So to me, that's a huge advantage. We also have the ability to run trade-off analysis, and this is true for the structural analysis, the CFD analysis, and the electromagnetics engineer role as well. So essentially allowing decision makers to choose the best design based on different data and different parameters. And with our structural and CFD solver, we also have a parametric solver. So being able to take all the different parametric conditions, whether it's simulation parameters or design parameters, we can also vary the design to get the best results. And then, of course, right, that future scalability to other 3D Experience roles. So our goal is, having all these solutions on the platform and enabling all these different solutions to work together, right, to build that cohesive environment, for team collaboration as well as data management, right, makes it so much easier. So taking a look at what this looks like, so you can see right within the 3D Experience platform, we can launch that CST Studio Suite. So that's one difference of our electromagnetics solution, is that instead of running it in that 3D experience interface, we actually run it directly in CST Studio Suite, right? So CST Studio Suite is known to have a very, very clean and sleek interface. So today we are still going to keep running our electromagnetic simulation on the CST Studio Suite user interface. The advantage of actually having it linked to the platform is that all our data can be accessed right from the platform. So the same data that you run your structural analysis and that you run your thermal analysis can be used right within CST Studio Suite to run your electromagnetics simulation. So let's take a look at the results here that we have for our BME model. So this is a far field type of analysis for a 2.4 gigahertz frequency, right? So if you think about frequency, there's different frequency ranges today. I think for our like Wi-Fi routers, we have like 2.4 and 5 gigahertz, right? Different range. So we can, kind of the same idea, we can test for all of that. Here's an example of running the electric field magnitude at 65 gigahertz for the entire model here. So you can see that we included the speakers, the body, the chassis, the battery, the electronic components, the PCB board. Everything is here, and we ran it on the entire model itself. Now, this I would consider a pretty heavy analysis, right? So just like the other solutions we have, we also have cloud computing and additional core local core access to run these high level simulations as well. Now, when we think about running simulations, we can also run simulations for future concepts, right? So, the BME, the original BME had, that one antenna, right? So it was on one side, but what if there was some interference on that side, right? So a future concept is perhaps breaking that one antenna into 4 separate antennas to provide better coverage, right? So just being able to run these what if scenarios really gives you and enables you to innovate, right, for future products, right? So maybe next year's version will have, you have 2 versions, right? You have the one with the 1 antenna, and then you have the one with 4 antennas. It's slightly more expensive.
So
but
this leaves the door open for future ideas and just allows you to get up and go fast on those ideas as well, without having to redo or reproduce any efforts that you've already made.
Yeah, I mean, that's the whole idea, right? When we think about engineering, we want to just kind of continue to build on the innovation that we already have integrated into our products, right? So, like a BME projector like this is really ahead of its time. And just being able to continue to innovate that and test all these different scenarios with such a small release cycle, that's really where this platform is going to be a really good fit for that engineering environment.
Absolutely.
All right. So with that said, I just wanted to provide this link to all our audience, right? So if you want to learn more about everything I showed today, you can actually just go to www.solidworks.com/simulation, and you'll find all the simulation tools we have, whether it's desktop or 3D experience. And you can also go to my.solidworks.com and sign up for free. And if you search Simulia, you will find blogs, white papers, videos of all the solutions that I showed today. So I just want to quickly wrap up. What the 3D experience simulation provides us, right, from a business value, right? So delivering delightful consumer experience, right? So when we are putting out consumer products, it has to not only look nice, it has to be able to work good, work great. We typically it's used extensively, used every day, and just being able to run all the simulation and virtualize how it's being used early in the design stage is really going to give you an advantage over your competitors, and as well as enable you to innovate for the next next releases. Just being able to imagine what if scenarios. Reduce product development costs, right? So, when we think about product, physical prototyping is not going to go away. We need to have physical prototype to ensure that, the parts that we're going to manufacture, right? But our goal is to shorten that cycle, right? So we can get to the best design by the time we're in our physical prototyping stage. Imagine the amount of time and money we will save, with just being able to shorten that cycle. Innovate a broader portfolio, right? So that's super important, being able to give our consumer options to fit their needs, just like us with the 3D Experience platform, right? So we provide all our users with many different options with a broader portfolio to meet your engineering needs. Minimize rework and compliance costs, and of course, streamline communication between all the stakeholders, right? So, today we focus on simulation, but the platform, enables uh, marketing teams, sales teams, strategy teams, operational teams, manufacturing teams, all to work together, right? So this is, when we're putting out a product like this, all of these teams are equally important, and having a platform where, we can work together to put out the best product is super important. That's it. I wanted to thank everybody for joining me,
Absolutely.
and let me show
Yeah,
you
thanks so
some
much
today.
for joining us. I mean, whether you're doing CFD, structural analysis, or electromagnetics, I mean, the 3D Experience platform, what I took away from that is, allows everybody to work together and on the same data at the same time. So it's really nice. That was definitely a refreshing presentation. And again, thank you so much, Sashi, for joining us. We always enjoy having you or any of your team members, honestly, on our show. We had a lot of fun last time too. So, and thank you everybody for joining us. Gian, do you want to close us out?
Yeah. Yeah, if you want to learn more, you can go ahead and click the link in the description, and that'll take you directly to the place that Sashi was mentioning, that solidworks.com/simulate. There's a link to that in there, so you can go learn more. And as always, special thanks to Sarah Zuckerman, who's helping us with every stream, and Omar joined us this time to help us on the back end, making sure we can get all your questions answered. This stream wouldn't be possible without these two people right here. So thank you to both of them. And tune in again on November 11th. Another 4 weeks from today at 11 a.m. We will be back once again with another special guest. This time we're going to have Mark Peterson joining to talk about what's new with 3D Experience SolidWorks. So getting back to the basics here, getting back to our favorites, in 3D CAD with 3D Experience SolidWorks, and we'll check out what was just released in the last couple months.